Okay, so this is a extra session just to kind of either wrap up the project, get ready more for the final, a chance for me to maybe make some comments on my review sheet, which will then get documented. Because if I write on it any notes today, I will also publish that as a separate marked up version of the review sheet, which hopefully I can get up later this afternoon or late or this evening sometime or another. So I stepped much closer to starting to grade the first project, but it's so time consuming to configure everything. I have a lot of things configured now, so I can just start grading quickly, but the problem is I'm only grading a few papers and then I have to learn the rubric for yet another assignment. So it's going to be a tedious process, but I will probably go after project one here, but I have things like that to do for every class. This for sure is the class that I've not done any of the traditional grader type grading because I just didn't get to it. And I was spoiled the last few years. So I really haven't posted anything new, but if you've been following the class on Slack, you notice that I posted up a new version of the final project because I didn't have something in the appendix in the appendix that was consistent, and the student that made that request said that that was helpful to them, so I don't know if it was helpful to anybody else. Chris, you've posted things to me a few times. I think I'm inclined to want to talk more about the project before I go and talk about more of the review of the final, because I just want everybody to have that well in hand.
That'd be great. I mean, I'm pretty much already done with the project. I just wanted to make sure that I actually did everything the way you expected.
Okay.
It's pretty much.
Well, I mean, you made some careless errors along the way, which hopefully when I pointed those out to you, things came back into focus almost
Yeah, no,
immediately.
it worked out really well. Appreciate the help.
Okay. See, the thing about teaching this class is I've taught it a lot of times, and I keep modifying the project and I keep tweaking on the project, and then I use the same core document, and sometimes I don't put things in. I mean, the last couple of times I've focused on, what we're focusing on now, but in the past I'd focused more on this, or I'd focused more on that. It was kind of all in the same realm of digital comm, but this time around I've got some more interesting things to do with impairments and plotting waterfall curves, which I think is good exposure for people that will work in digital comm. And the way most people work in digital comm, when they're a junior engineer, they're in the lab taking measurements and collecting data on a system and trying to measure performance. So that's part two of the project. So I'd like to go start somewhere on the project, but I need some guidance as to what you want me to look at. We've talked about part one in the past. Is there anything I should be wrapping up on part one that anybody would like to see?
Oh, I was going to say something, but maybe I shouldn't.
Well, ask a question. You're not giving an answer, just ask a question.
No, frankly, I'm lost. And I'm
Okay.
part one, and I just started. So
Okay.
I think what I probably should ask you is a more relevant question for the class overall. At some point, I'm run out of time. I
Yes.
knew this was going to happen. Something had to give, right?
Yeah.
There was just too much going on.
We all have that.
So yes,
No one's
that's
immune
fine.
from that.
No one's immune from that. I got problems here trying to set up stuff for my wife working at home, and it's just taking a lot of time.
Chris will help you with
So
that, right, Chris?
Don't put more on my plate. You know how full my plate
But
is.
I remember at the when this COVID-19 stuff started, you told me you had to set up space for your wife and then your mother-in-law, and then I know you were homeschooling, I'm sure too. So things got pretty chaotic at your house.
Oh yeah, no, I've got basically three different or two offices and a classroom now. So it's been an adventure getting here, and we're planning on it being this way at least through June.
Yeah.
So
yeah.
Okay,
So we all
so
have that problem. So I'm just wondering, basically, if at some point I'm not going to be able to finish the project. I got to study for the test. So
Well,
what
I can
should
make
give more
I can
emphasis
make
to?
exceptions. The thing is I don't want people shooting themselves in the foot unnecessarily. I mean, if you are out of time, I can extend it, but the idea I can't extend it very far though because I already know what my deadline is, and it's not any
Right.
different than it has been. I don't have to go to graduation, so I guess I'll have a little bit more time on Friday to be doing grading. So we can talk on our private channel about what you think would work for you. I'd like you to spend more time studying it because the first thing I ask most anybody that comes to me in private saying, "Can I get more time?" And the first thing I'll do is, "How much more time do you need?" And then we'll negotiate how much I can give you, type of thing. So
Getting more time is fine, but my real question was, where should I put the emphasis? Should the emphasis be on studying for the test versus the
you have
project?
to make that decision. I won't make that decision for you. The exam is going to be just like the second hour exam. It'll be open book, open notes, and I don't know whether that means you're going to print everything or whether you're going to have it so that you can look at the notes on your computer. I would personally make the recommendation that I don't really want you cruising around on the internet. That goes for everybody. But I would personally recommend that you have things on your desktop. So if you have to bring up
Yeah.
chapter 4, or not chapter 4 because we didn't really study the digital, well, we did 4, 5 we didn't really go into because that's what the project is covering. But you can bring those up quickly, and then other such things like solutions and things of that sort that you might want to look at. And then, of course, the book, if you have it in PDF form, you have to bring that up on the computer. If you have a paper copy, you'll be able to bring that up. But I use my notes when I'm working pretty much everything because it's a little bit more condensed than the book. And the book is good for studying, though. It's got really good review sections in it, I think. I like that part of it.
Okay.
So
So
I wouldn't
overall,
I wouldn't dive in and say as of this evening you have to go full force on studying for the exam. I think you should be working on the project and getting the lay of the land a lot better in hand because
Okay.
there's not going to be that much time afterwards either.
Yep. I just wonder what's worth more. Is it really the exam or is it?
Well, if you know how I'm letting
make an
things
informed
float,
guess.
they can both be worth equal, right? The
Yeah.
final can be worth between 25 and 30%, and then the two projects together can be between 20 and 25%. And of course, I optimize that. So it is important. I can tell you right now, and maybe some people that are willing to give testimony will chime in, that the second project is a lot smoother to get through. When you finally get into it, there's not as much to do, I don't think. It seems like it goes faster. And I'm sensing this. I've had people tell me this before, and I'm sensing it again this semester too. For some people,
I definitely got through the second project a lot smoother than I got through the first project. I'll testify to that.
because you don't have to write the code to process the waveforms to the same detail level that you did before. So it does go faster, and I think it's more fun too, just because you're doing these different things with digital comm, and you should feel empowered. You're converting analog samples to bits, sending bits through a pipe, error correcting them. And then I have you look at some impairments, phase noise, timing error, which are pretty interesting topics, and the waterfall curve topics are pretty interesting too. So
Okay.
just kind of get the lay of the land and then maybe come and ask me about it. So, okay, so if you're not ready, and I'd rather go with somebody who really wants to review some of the problems. So where should I go, Chris? Because you started to say you wanted to double check some things. So let me know what you'd like to double check. Part 1. Part 2.
Just give me one sec to pull it up on the side real quick,
Okay.
if you don't mind. Okay.
And Jared, you're out there. I know your microphone doesn't work very well, but you can Slack message me. I've got my solutions up on my other computer here right now.
So there's a few things. The graphs on, where is it? Come on, get to it.
Just call me the
the
task number.
4A and 4B. I wanted to make sure that we're graphing things appropriately, and then also, well, I mean, all the graphs on the second part, I want to make sure that we're getting right. I have some questions about 5A and B that I don't know if I asked them explicitly, if I'll give away too much information. So,
Well, if it gets too sensitive, then I'll just say let's have you ask me on our private
Okay.
channel afterwards. Okay, starting
Right.
with number 4, though.
Yeah, let me
Getting
put myself
introduced
on
to
mute.
waterfall curves, and I'm going to go look at my solutions for task 4. Task 4 has got starts off making a collection of 5 scatter plots, and the scatter plots that you make in there are just going to be using the simulation framework that's in there, but they're going to be I think, yeah, the signal to noise ratio is fixed at 20 dB. And actually, it adjusts. It steps down, right? I'm thinking, no, it's fixed at 20 dB, but it changes every time you change the number of bits per symbol in the quadrature amplitude modulation scheme. So you're going to get, I have to go back up here to where the first and really only plot that's kind of similar is. So you're going to have 5 plots that are this type of appearance, except it's going to start with just m is equal to 2 that only has 2 dots in it, or 2 scattering points, one at -1 and one at +1 on the real axes. And then you're going to go with m is equal to 4, and you'll have 4 points. And then, I used a subplot array, just like you could do in MATLAB. I did a 3 rows by 2 column subplot array. So in the very last row, there's only one plot. But then there were four clusters in m is equal to 4, 16 for m is equal to 16. Then you'll have this plot here for m is equal to 64, and then you'll go up to the extreme of 256 points, which is a very tight, dense looking thing.
Yeah, so that's kind of, the 256 it loses a lot of fidelity, especially at the scale you have us with our figure size.
Yeah,
Or with our 6x8 figure size, and then we have them all nested
yeah, subplots.
inside there. Yeah, so I mean, it really, there's at least in my result, there's no fidelity between the clusters.
Well, you could make the figure bigger, or you could play, if you want to give me individual ones, I don't care. It's just going to take more. I mean, you're not turning in papers, so I guess it doesn't really matter. They are very close together, though, and 256 QAM, as it's known, is the most dense constellation that's part of cable modem technology that we use if we use
So if that's an option, I would prefer to use larger
Okay.
plots personally.
Okay. Mine, I mean, I'm looking at mine right now, and mine was done as I suggested, and yeah, it looks like the clusters are touching, and in reality, they are. I mean, it's so dense that the 20 dB signal to noise ratio is not good enough, because as you see when you do the waterfall curves, which comes in part B, you can see that the 256 QAM, the theoretical EB over N0 of 20 dB, puts you at an error probability that's about, I don't know, 4 times 10 to the minus 4th. So there's a fairly high probability of bit error going on at that point. So it needs to operate. If you want to operate at a lower error probability, you've got to have a higher EB over N naught, as you see from when you do that part B waterfall plot. And the waterfall plot is done using the function that was not properly explained in the appendix. It was an older function, but everybody should be using QAM underscore BEP underscore THY, BEP theory. And then you just put in a range of EB over N naught values in dB. And then the second argument is M. So M just has to take on the values that you want to be using. 2, 4, 16, 64, 256, and then you overlay your plots. I used a legend so that there's a nice legend to show what each different color is.
Okay, so just to be clear, were you expecting one single plot with 5 different, or technically 4 different
It's 5
lines, or
5 lines, yes, all in one plot. So that way you can
Okay.
see how they stand with one another. One pair lines on top of the other one, so that's okay though.
yeah, we have to explain why that happens.
Yeah.
So, and I think I understand why,
Okay.
but I still have to get that down in writing. I don't know. So I
I'll
did
give some
5
hints on part C though, because that's an interesting discussion right there, which kind of is, in my mind, is motivated by the pictures that you have in part A. So when you look at your pictures from part A of task 4, and then think about probability theory in these clusters, what do you see that seems consistent? And that's the way I did it. I actually went off and did some histograms, which you can do too if you want to. From your scatter plots, you could go launch into doing histograms if you wanted to, slicing in the horizontal axis and the vertical axis if you wanted to too. And then you'd see histograms that are bell-shaped curves, and then that'll help explain things better too. Probability and stats wasn't a requirement for this class, but by this time I can't believe there's anybody that hasn't been through enough to understand that aspect of probability theory.
Professor, this is Tanjit.
Yes.
Okay, so I'm still working on part 1, and part 1 looks not that complicated, kind of self-guided, so I couldn't able to jump into part 2 yet.
Right.
So not enough question from part 1 because it's just a lot of question marks that I need to fill out on your coding.
Okay, so what do we want to do? Do you want to jump back up there, or do you want to continue on part 2 for the time being until we kind of get to the bottom, and then we can circle back
Yeah,
up?
you can continue at part 2. I don't have any questions right now. That's what I'm asking you.
Not on part 2, but you do on part 1. Is that what you're saying?
No, part 1 I kind of figured that out
Okay.
mostly, so I'm okay.
Okay, well, if you're like Chris and you want to make sure you have an idea that you've done the right thing, we can go up and look at anything up there.
All right, I can let you know.
Since I'm moving pages around, understand that all of this error probability estimation that you do in task 5 and 6 is being done with functions I provide, but it's estimating the error probability using repeated trials type experiment, or known in the business as Monte Carlo simulation. So that's what the bit errors get divided by the total number of bits that are processed, and then that forms an estimate of the error probability, which we would call repeated trials in an experiment. Right? Does that bring back memories for anybody? Or if you play a board game and throw dice
yeah.
and all that other kind of stuff. So, or spin a spinner, various other things that are in games. So, okay, next thing, moving down the line from you, Chris, in part 2. Anything?
Yeah, no, I think I got part 2 just fine, personally.
Okay.
I'm pulling it up. Oh yeah, no. Task 2, you and I went over ad nauseum, and then of course I had the issue where my notebook went to hell, and I couldn't figure out why, and I just started everything over. And actually, the second time I did, I liked my line a lot better. So
Okay, that's good. How about on task 5 and 6? So that's where you're doing impairments. So when you get down here at the bottom,
yeah.
there's some kind of
So-
interesting things in there, I think. Task 5 has you look at phase noise sensitivity. So what phase
so
noise
basically,
is
we're
doing.
just looking at where our measure deviates from the theorized waterfall curve, correct?
That's right. So it's this. It's the same idea that we have here in the symbol timing plot, right? Symbol timing sensitivity plot that we'd have up in here. It's going to.
See, now, it might
It's
have
gonna
something to
flare
do
out.
with how I have my graphs scaled, but I don't have nearly the same inflection angle that you have shown on your example there. Mine are a little bit flatter, but then again, I'm also only showing, like on part 6A, 10 to the negative 6 to 10 to the negative 3 on my y-axis, and on my x-axis, some 15 to 20 dB.
Okay.
You don't have your lower axis there, so I guess conversely, I'm about the same as you. I don't know. I think it's all up for interpretation. Plus, I had to draw horizontal lines just to make sure I could get that that deviation.
Yeah, I'm
at,
going to make a comment about that for everybody. So on part number 5, you have something. You have the waterfall of the ideal theoretical system, and then when you plot some data points with either 1 degree or 2 degrees of standard deviation, you're going to get. Let's see. I'm trying to pick the colors that I was using in my solution. You're going to get things that look kind of like that. Not as shaky as I just drew, but you'll have something that's fairly close to theory with only 1 degree of phase jitter. And then when you go up to 2 degrees standard deviation of phase jitter, it starts to flare out considerably. And what's happening here, the reason why this flaring is happening, is because if I was to go back up to the scatter plot that is in here, what's really happening when we put in the phase jitter, we have the rectangular decision grid for deciding points that land in the 64 blobs there. But when we put in the phase jitter, the whole scatter plot we're looking at is kind of jittering back and forth. It's rotating with a Gaussian type distribution, clockwise and counterclockwise. So the points are getting smeared in a rotational sense, and they're going to be more likely to land in a neighbor's decision region. And that's what starts to make the errors go up dramatically. If you remember back in the beginning of this document, it shows you what those decision boundaries are in the very beginning, and they're right here. So just imagine if those red dots are getting kind of circularly smeared because of the jitter, making the carrier phase not be perfectly clean. It's going to, that with the Gaussian noise on top of it, is going to make it start to fall into an adjacent decision region there, or an adjacent square. And phase jitter is a characteristic of oscillators. It gets imparted by the phase tracking system in the receiver, but it could also be phase noise that's on the oscillator that's going to impart some of this degradation. So it's pretty important. You got to use quality oscillators, as it turns out, but then the phase lock tracking mechanism that tracks the carrier phase has to be good too. That's kind of what my other class in phase lock loops has dealt with. This is in the appendix. It explains it for the binary case where you've only got 2 scattering points, but it talks about rotation in the jitter. This talks about it being in a static location, but it's actually rotating. It could be rotated here with, in addition to the noise cloud, it would have the jitter that would be in there too, which is what we're modeling in this other part. And then the last task, besides playing speech all the way through and decoding it back out to speech again, this one is timing sensitivity, and if you don't make your decisions at the right timing instant, and there's a picture of that in here. This is with a square root raised cosine pulse shaping, but if you time just a little bit off, like if your timing was coming down over here or on this side, you can see with this pulse shaping filter, which is trying to keep the bandwidth really narrow, as soon as you move off the optimum timing spot, the eyes there start to close up, and with noises present on top of just the filtering effects of the square root raised cosine filter pair, then you're going to start to make errors, a lot more errors very quickly if the timing isn't maintained properly. So this is another type of impairment for a digital comm system. And it's the same idea, though, as with the phase jitter. It just makes the curves start to flare out pretty rapidly. So with regards to the flaring out business, there's different ways you can handle this. I want you to get a data point above and below the operating point. So here you're supposed to be operating at 10 to the minus fourth. And so if you get 2 measurement points, as I've got shown here with the red dots, then you have to do some interpolation. And because the points are going to be fairly close, you can use linear interpolation if you want to, and that's what I did. I wrote a little helper function that I could put the coordinates of the 2 red points into, and then I could put in what x-axis value what y-axis value I want. So I could put in, 10 to the minus fourth, and then it would linearly interpolate what the x-axis value is at that point, and that's how many dB you are away from the theory at that particular error probability, which is usually a requirement on that. That's the way the customer would give you requirements on your system. It has to have no more than x dB of degradation or x tenths of a dB. So that's why this is kind of a practical question.
What I ended up doing on that, Dr. Wicker, and tell me now if I have to redo it, but I had Python draw a line between the 2 points, and then I drew a solid line across at 10 to the negative 4, and you can see, at least I think you can see fairly accurately within about a tenth of a dB where they land, because I also turned on the minor grid as well as the major grid.
Yeah, that's fine. That's done totally graphically, but I did it by just linear interpolation, and that works too. I think I might have worked mine in the log domain too, because of the fact that this axis tends to be, well, it's a semi-log axis, so I would convert in my linear interpolation, I converted all the 2 probability values to log base 10 of the probability values, and then I use that for the y variables in the interpolation, and then work that backwards to finally get the x-axis value. So I had the x-axis values in dB, and then I had the log base 10 of the probabilities for the y. And I always think back to high school or earlier when we had to learn how to do linear interpolation. True? Do you remember having to do that somewhere along the line back in maybe high school or middle school? I mean, I have a vivid memory of it, and it's a good memory. I mean, it's just like that was where that became a routine of just being able to do that.
I mean, I had to do it for work all the time out in the field, so that was pretty much where mine comes from.
Okay. When I'm doing other things, though, I can use numerical techniques too, and there's root finding techniques. But here we don't have enough data points, so we just have to do a linear interpolation is what I do to get that. But what you did graphically is also fine. So that's the idea. And then the very last part where I say play through the audio loop, or do an audio loop. The challenge there is just to make sure, and the way this problem works out, it's not that ugly of a trap to fall into. I mean, you're not that likely to fall into it, but the thing is that there is going to be some delay in going through the system, and what happens when bits come out at the other end, because of the filters that are involved, the match filter, you're going to have a region when your data bits first come out and get decoded that are nonsense because you've got these filters that had to charge up and everything. And the filters that I'm using in there are 2 square root raised cosine filters, and each of them have a average or mean delay of 6 symbols. So they each have a delay of 6 symbols, and so that's a total of 12 symbols that are going to get delayed. You're going to get delayed by. And if you're encoding at 8 bits per symbol, which is what you have for 64 QAM, things are going to get decoded. Every symbol gets decoded back out to 8 bits. But then if you're using PCM encoding for the audio, that's 16 bits per sample. So the important thing is when you're back down at PCM would be 16, 16, and these are at the bit level. The important thing is to make sure you don't feed into the PCM decoder something that is straddling kind of like that, or I guess drawing it in there like that. You got to make sure that the very first 16 bits that go into the PCM decoder are lined up on an edge of the 16 bits that are required from the original encoding at the transmit side. I just want you to be cognizant of that fact. That's a framing error, and I give an example of that in this document of what happens if you don't frame properly. So you will know, and you're going to take a screenshot of this. So that's what this example was about right here, where I purposefully did not trim the data properly in the second case. So I had it skewed by a couple of bits in framing things up into the 16-bit blocks, where here is I had it correct. And you'll know if it's right or wrong, because if it's not right, it's going to sound very messed up sounding, like it's got a huge amount of errors, but it's just a framing problem on the 16-bit words. So that's just something to watch out for. As I'm recalling, nobody usually has a problem with this because everything pretty much falls into place at the end here. But if you do have a problem, it's because you're not framing it properly. You've added some extra samples in, or you haven't trimmed properly. So that's what I'm doing here, is I'm taking the data that comes out. Let's see, it stopped working. I'm taking that out and I'm just trimming it to the right amount. And I discussed that in here, so I don't really want to go into that in a lot of detail, but this just explains what's going on there. It's all integer arithmetic, but you just got to get it right so that this comes out properly. And you're gonna listen to it, and you'll know it's sounding pretty good because I don't have it running at that low of an SNR that it shouldn't have very many errors. I said running at 100 dB, so there's going to be no bit errors in the link at 100 dB, even with 64 QAM. So it's got to sound really clean. If it's not, then you've got an alignment problem, like I'm showing down here at the bottom of the page. Good.
Yeah. So on that, if so one of the things that we should see is that bit error at the very, where did I put it? There it is. At the very front, where you have the messed up bits when you have that due to
The time delay and the filter getting charged
yeah.
up.
The propagation delay or whatever.
Yeah. Group delay
So-
actually is what it is, and through the filters. But
Group delay. Yeah. Okay. So yeah, because I'm showing on mine basically a verbatim duplication of the original of my recover signal from my original signal, except for the first few samples are way out of line.
okay, and then you just trimmed those off and then fed them into the PCM decoder, and it came out sounding fine.
Yes.
Okay. The other thing is the PCM decoder expects the number of bits going into it is an integer multiple of whatever the PCM word length is. So in this case, it's going to be an integer multiple of 16. So you'll have to, if you have to trim some off the front, then you have to maybe trim some off the back to make sure that what you're actually giving it is an integer multiple of 16. Because I think it gives an error if that's not true. But again, you'll be able to listen to it and hear what's going on when you play the audio back. All of this stuff gives you an appreciation for what has to happen in a real system, and there's still even more that has to happen, but these are some of the things that have to happen. Whereas when you did project number 1, everything was analog signal samples. It didn't really matter there, but now that we're in the digital domain, we have to think more about what's going on. So that's what I like about what I'm having you do. It's pretty much common sense, but until you're actually there playing with it, you don't really appreciate why it's so critical, because it's kind of like there's only one right way to do it, and if it's not right, it's not good. Okay, so I can go back up to part 1 if there's anything that you want to ask me about part 1. I did add this change. Decided I would increase the channel signal to noise ratio up to 200 dB, so there's no chance of bit errors at all going through the link, and the only errors you're going to get are due to quantization noise in the system. And the reason why I increased that, though, I decided to be on the safe side, is when we go up to 16 bits of PCM encoding, that's pretty much, well, that's the compact disc digital audio standard. And they say that the signal to noise ratio is around 100 dB, and that's what you should be seeing in your results for that value. If I'm thinking back to my result over here, yep. You should be getting about 100 dB in your 1 over MSE and dB plot when you have 16 bits. And I decided with the channel signal to noise ratio at 100 dB, you might, it still shouldn't make any bit errors, but I decided maybe it was overkill. It was based on what the experience you had, Chris, but
Yeah, so that's
it doesn't hurt. It doesn't hurt anything now. 100 or 200 is like, no one would have that high of a signal to noise ratio in a digital comlink channel. But
so after I went back and restarted my notebook, I got perfectly good results at 100
okay,
dB.
so I'll probably change my writing back to 100 because I was just getting jumpy when I saw that. I thought maybe I messed something up. But as I think about it right now,
it was me.
the waterfall curve is going to be, the probability of error at 100 dB in that system is 10 to the minus hundreds and hundreds. It's like it's never going to happen. There's never going to be an error at 100 dB. But 200 dB is just going to drive that waterfall curve down to bedrock and to the center of the earth, basically, in terms of probability, log base 10 of probability, a very large negative number, or not a negative number, but a very large power, negative power, 10 to the minus hundreds and hundreds. So that's essentially zero, no probability of making an error. Okay, so
How do you get the number of bit errors?
how do we get the number of bit errors? We
Yeah,
we have some
I keep getting
functions.
0.
Well, this is
I
in
am
part
lost.
one.
That's what it is.
This is in part one.
Yes. Oh yeah, at the very beginning, part 1, task 3.
Okay, so you've got a function that provides the bit error calculations, and that is I have to go back up into here.
Yeah, hey John, just say no. I ran into that same problem too until I finally stumbled upon it, and then it kind of
Yeah, it's
fell.
right there in the middle of the page. He just passed. Yeah, that's where I was at. Right where the question marks are.
Okay. Yeah, this is in the analog domain. The MSE is based on the analog samples, but the bit errors are based on errors between D and D hat when you run through this system. So
Oh,
let's just do this really quickly here, because I think I have to get some data to go through though to run this.
Yeah, and that D and that D hat thing hung me up for almost an entire half of a day,
Yeah,
just trying to figure it out. Because I was trying to go between M and M hat instead
M
of
hat.
D hat.
these
If you
are
do-
sample values. You want bits though, and the bits are D is what goes into the channel from the encoder, and then D hat are the bits that come out after it's gone through the additive noise channel. So down here when you do
Okay.
this system,
Also, one more question is if you run something with noise in,
right?
where's the AWGN, you get a different answer for this noise ratio, and it is significantly. Why is that? Is it because it's running off a different?
I think I need to
Sometimes
understand
you-
better
sorry.
what you were doing, but let's see. I have to put, in order to run this example, I can play with this example. I think last week, wasn't I putting in, I was playing with this. I'll put in this one, the cosine wave, for my speech. So let me think. I think I can run this through right here. So now if I go, this doesn't ever work when I'm running this video recorder, but if I go look at D, those are my ones and zeros, and D hat are my ones and zeros as well. So we're calculating bit errors between those two arrays, and I'm just going to do something. What are the lengths of these right now? See if that's 3,200, so that's pretty long. I'm going to do something that you haven't seen before, but I'm going to use a plotting tool called strips, which is kind of like something that's in MATLAB. There it is, strips. So I'm going to take and form a strip plot out of D hat minus D. So the values that I can get if I subtract these two equal length arrays, because they are equal length because they go in and come out through the encoder and decoder, are going to be zeros and ones. So when you subtract a 1 from a 0, I get a -1. When I subtract a 0 from a 0, I get a 0. A 1 from a 1, I get a 0. But then a 1 minus a 0 is going to 1. So it's going to be a 3-level value, but I don't want all of these in here, so I'm going to go up and do about 200, let's say, and then I'll do 200. Have to do the same number over here if I'm going to subtract them. And then in strips, shift tab, how many rows do I want to have? So how about if I do 5 rows, and that will be 40 per row. I could do 10 rows. I don't know. I'll just try a number here. See how that looks. No, that's too many. I can't see what's going on there. I did that wrong. There. So I know that there's one bit error in here, in this little short segment that I'm looking at right now, but I think I need to make this be about 50, and I need to make this be about 1,000 probably. So I've still only got one bit error in here. Let's see, what am I not doing right? This is at 60B. You went through this already. I'm just trying to be a more illustrative thing here for what I'm putting in. It's not illustrating what I want it to illustrate though. At 60B it should have more errors than that. Now it has a lot more errors at 4dB. I just wanted to illustrate though that if we're looking at the bits, we can see that any place we're not equal to 0, if we either have a blip down or a blip up, that's where we've got a bit error in these first 1,000 that we're looking at, first 1,000 bits. Whereas if I was to compare waveforms, it's not going to be anything like that, right? If I did something totally wrong, like put in M times scale let's see, I'm just trying to be creative here, scale times that. Actually I don't have to do that, I can do it that way. Then this will just be M hat over here. See, these are analog samples. These are, and yeah, they're not the same, but I wouldn't expect them to be the same. There are bit errors in here, though. You're right, but notice that they're not. This is not binary anymore. It's continuous values, and yeah, this will have less differences when I run at a higher cylinder noise ratio. But we're not counting bit errors. We're counting more like mean squared error kind of stuff. So it's just not. It's just wrong. It has to be the digits that have to be in here. And there we got three bit errors are showing up at 6 dB right now in this particular run out of the first 1,000. But I think you'll find there's a lot more bit errors when you get done. And I ask you to just, let's see, what did I ask you to do? I asked you to come up with a simple counter, I think. Yeah. And just look and see what I did here in this problem. Yeah, I just have you count the errors, so you can count the errors with math, kind of like what I'm doing right here, except you just want to do some simple math on this. You want to count wherever there's a deviation from 0, you want to get a count of 1, and then you want to add up all those counts. So you're going to use some NumPy math in here to get the total error count. Make sense?
Yes.
Okay.
Once I figure out what that function is.
Well, it's going to be simple.
That might take me an hour. Yeah.
Well, I'm kind of
just
giving you an idea right now, though. You see, you've got positive and negative blips, and if you can convert those to be positive blips, then you can just add up how many blips you have. And you can use NumPy math. You don't have to use a loop or anything. So, what else on part 1 that anybody wants to review? We're going to run out of class time here, so we need to switch over to the exam pretty soon.
Yeah, I haven't got much farther than that.
Okay.
So nothing you can do.
Anybody else have any questions? It's in the session right now, and I'm not even sure if we still have 4 people up or not. You guys are looking at the screen. Are 4 of you still here?
Yes, I'm here.
Okay. So, Tangyit, do you have any questions?
No, not right now.
Okay. Be sure to fire things at me, because I'm not always going to be able to answer, but they accumulate. And really, Phase Lock Loops meets tomorrow morning, but half of the class has turned in their take-home exam already. So most of the action that I have to tend to, I want to grade papers, of course, but most of the action is all from this class at this point, I think. I still have some cleanup to do in that class, but this is going to be where most of my action, I expect most of my action here. Okay, so I'm going to switch over to the review sheet. The first thing I want to do, though, is just look a little bit at the exam, because I said I would contemplate making sure I revisited something. And I was disappointed on these problems, but I can't revisit them all. Number 3, I got disappointed on because there was a lot of ignorance that went on in some people. They just didn't notice that there were 2 local oscillators. So I feel like I want to do something with, I might put another dual conversion question on here just so that you can understand everything about the images, and it relates to the front end of the system. So that's the job of the first local oscillator in the first conversion stage. That's where all the susceptibility to images comes from. The second conversion stage in a dual conversion is to get selectivity, so you can take things down to a second intermediate frequency so that you can get a much narrower bandwidth as needed. And in the case of this example, it was for the narrowband FM that's used in the weather radio and other two-way radio services. You can't easily design a narrow bandpass filter at 10.7 megahertz that you'd like to have you'd like to design a 5 kilohertz bandwidth filter or 10 kilohertz bandwidth filter. So by going down a second time, you can more readily get that narrower filter built. That's my understanding, and that's been my experience, but maybe somebody else has another opinion.
The Qs are very high if you want to do it the first way.
Yeah, and
So
then
that's
you
why
have the
they've done
loss.
part of-
You can't get
Yeah,
the
there's a
high
lot of
Q
loss,
because
too.
you have the losses. So,
Yeah.
but there is the potential for driving a signal through at an image with the second IF, but this class is not on receiver design and all those specifics that a RF front end designer might go through. It's just on the basics. So I'm very inclined, though, to at least ask about images and conversions. Maybe it won't be dual conversion, but I just want to make sure you get this correct. And I really like it when you draw a sketch like I did in my solution, where we can see where the image is. In this case, because the local oscillator was high side tuning, the image is going to be above the local oscillator by the first IF frequency. And then you had to choose the second local oscillator. I said it was to be chosen as low side tuning, whereas the radio modulator used in the lab is very much this architecture. It's very similar to this, but it uses high side tuning. So there's a crystal oscillator in that receiver, if you remember, those of you that were in the lab, that's at the high side frequency, which is 10.7 plus 455. This frequency, if it looks familiar to you, it's an amateur radio frequency that I learned when I was very young, because my father always talked on 2 meters FM, and this was the usual call-in frequency that he used. All his amateur radio friends used, and then they would maybe do something else, but 146.94 just got locked in my brain at a young age. Nobody's an amateur radio person now, right?
I am VHF band.
Okay,
right?
so do you use this still?
Yeah, occasionally. It's been a while since I've done it, but yeah, I noted that one. I saw this before.
Yeah, it's in my vocabulary because, let's face it, if you're a really active amateur radio person like my father was, the whole family knows about it because it's everywhere. It's at home, interfering with TV. When we go driving, he had his antennas in goofy configurations and the multiple radios in the car. Stop. He's got his radio pulled out. That was before cell phones were that common, so I just grew up with all that.
It was probably, imagine it was probably a repeater frequency, wasn't it?
I don't think this was, but there was the
okay.
repeater frequencies. Yeah, then the repeaters became popular. It's a whole lingo thing. So just cruising on down here, the next area, This problem I won't repeat, but it was annoying to me because of the fact that a lot of you picked a really high frequency and then you doubled it, and it was essentially almost right on top of 101.1, and then you made a really low frequency local oscillator to just move it a small amount of frequency. And whenever you multiply one signal times the other, you always create the sum and the difference. So this filter then would be very difficult to build to remove the unwanted frequency if you just move it by a small amount. So I gave you all the degrees of freedom, and then you took those degrees of freedom but made some poor choices. I really didn't take off points. I wrote on your paper though, like, this really wasn't a very good choice. It's not practical to do that. This filter would not have been practical for a number of people's papers because it was just not very well separated from the sum or the difference. Let's see. That was fine. Phase lock loop, I won't try to do this again. This was kind of a disaster is what it was. So I don't know about phase lock loops in general. I'm now going to want to just jump over and look at the work from the review sheet. But I gave you one problem for sure that I'm going to revisit, and that is basic superheterodyne and images. And because I have a repertoire of old exams, I definitely have a collection of old exam problems. So I don't have a problem coming up with something. And if I dream up something new, I can also go with that. So I'm going to start at the top now since we're not super pressured. I just list the appropriate sections from the book. You'll have that at your disposal, and it's always been that way when this exam is taken. I was reading in the ASEE today that this is something that we don't have this problem, but apparently in some universities, students are getting very stressed out about having to work on exams like you will have to, but not open book and open notes. So people are going off and going to extreme measures of cheating, I think is what they were saying, and because it's very stressful. I'm trying to take that away by just saying, just have the material there. I really don't want you cruising the internet because I want you to focus. The time is what matters. So in the beginning here, though, we had just the necessary linear systems stuff to review. Signal models, periodic, aperiodic, phasors and spectra, singularities. I really don't have a particular question on the fundamentals. It's just that it will be integrated into a problem, and I think that's the only way that these things show up, is that they're integrated into an existing problem. Obviously spectra is really important in the class, so I could circle that and say spectra is never going to go away in this course because it's fundamental to communications theory. Having that spectral vision has always been there, and it will always be there. So that's what I've got written down to words. See, I don't even have to, shouldn't be using my brain because I already wrote it down. It's just going to have to be there. Classification, power, energy. They're just used in modeling waveforms in communication systems. So power and energy are what we're most interested in, and they showed up in AM where we had to do efficiency. They showed up in FM where we were looking at a signal going through a filter and then what part of the spectrum was eliminated, what part of it passed through. So those would be areas where power would show up. Fourier series, a specific Fourier series problem is not something that I would put on the final. That was getting us ramped up into things, but Fourier series ideas can be useful in working problems and being aware of harmonics and things of that sort. I mean, here's kind of an interesting idea. If I was to give you a spectrum of an FM signal, I mean an AM signal if I said it was an AM signal and I said it was tone modulated, if it was, say, on a 1 megahertz carrier and it was modulated with a 1 kilohertz tone, and then the spectrum was said to be double sideband, but you saw harmonics at plus and minus 1 kilohertz about the carrier and then plus and minus 2 kilohertz about the carrier, what would be a bother with that? You would say, well, I expect the 1 kilohertz, but why am I seeing 2 kilohertz? So that would come about as some nonlinearity, right? Something nonlinear was going on before it got to the modulator, or in the modulation process it ended up producing those harmonics. And that's not to be there, but on the other hand, if you're looking at an FM signal, we know if it's sinusoidal, the Bessel function sidebands are always going to be at multiples of that single tone frequency. So if you don't know what the tone frequency is, but you look at the spacing of all of those tones above and below the carrier, the closest spacing any of those tones can have is the fundamental frequency of the tone modulation. Do you believe that? I mean, I believe that to be true. So if I didn't give you a piece of information and working a problem and expected you to look at the spectrum and figure out what FM is, the sinusoidal tone modulation, you just have to look at the separation of the closest line spectra.
I would imagine there that any kind of distortion is going to be hidden by the Bessel function response to the tone modulation. Right?
Yeah, well, it would make it harder to see it. But
yeah.
The reason why a problem kind of circling around those ideas is kind of important to me is that when you're diagnosing a problem, you look on the spectrum analyzer and you see a whole bunch of spectral lines, and you say, is this caused by an AM amplitude modulation of some oscillator in the system, or is there some unwanted FM modulation going on, and what is the origin of it? So you can be kind of like a detective when you're looking at a spectra of what you expect to be a clean sinusoid, but then you see a bunch of sidebands on it. Something is leaking into it, and you might even be able to figure out the amplitude. This is more of a detailed question from the phase-locked loops class, where a voltage-controlled oscillator's control signal could get polluted with some other signal, but I don't know. I'm just talking a little bit about Fourier analysis, though, where you think in terms of harmonics. We did a lot with Fourier transforms, so they'll be, vital in understanding communications theory. So that's kind of what this bullet says. You will have access to the Fourier transform pairs and the trig identities, and there might be some needs to do some modeling in there. So just be aware of that. A specific Fourier transform problem like you would have had in Signals and Circuits 2, 3205, no. Power spectral density, not really anything hard driving in that area. The only thing is if I give you a power spectral density and wanted you to find out the power contained in some bandwidth, you should just know, the power spectral density, I just integrate over that interval and I'll get the power contained in that piece of the spectrum. And of course, if you integrate the entire spectrum, you get the total power in the signal. Working autocorrelation functions and that stuff, it's interesting and I like it a lot, but there's far more other things to ask questions on. So I'm going to go ahead and at least say a specific autocorrelation function problem, no. Maybe something with power spectrum and integrating related to power calculation. So I could put in here, and I'm going to be posting this up, remember, so. With area under curve. I'll just say maybe something to do with power contained in a band, and it would be something that would be easy to integrate, not some exotic thing or another. Linear time invariant systems, just necessary ingredients. So I would definitely say not planned at all, but an understanding of LTI systems is required. I mean, it's just there, right? When you have to, you're going to have to work an FDM, frequency division multiplexing type problem, and when you draw out the receiver block diagram, you pick filters according to what you understand about the spectrum, and that's understanding LTI systems, that you specify filter, bandwidth, and center frequency in order to pass a signal and reject other unwanted signals. A convolution problem, no, the only convolutions problems I'd be interested in would be ones that would involve delta functions that are very easy to manage. Sampling theory in the Hilbert transform, that was handled when we jumped back there from chapter 3, so if I decide to do anything, I'll be talking about that in the chapter 3 review, which is the next section here. So double sideband, amplitude modulation, and index, power in the carrier and the sidebands inefficiency. There will be a problem on this. I won't say specifically which type of problem, but there's something out of that in the amplitude modulation area. Hilbert transform problem, even though I was disappointed on the exam with the analytic signal, I'm going to say no Hilbert transform problem. If I was to ask you, though, which is more bandwidth efficient of these three, you have to answer single sideband, right? Because that only takes a bandwidth W, if that's the message bandwidth, whereas both AM and double sideband take 2W. So I can ask you that question, though. You just don't have to work the detailed math. Frequency translation and mixing. For sure, I've already hinted at that because that's what I was going over from the exam 2 and the images and that stuff. So there'll be a problem on that. Fundamentals of angle modulation, which now, chapter 4. Yes, it might be rather than what we didn't do on the exam was I didn't have you plot the instantaneous frequency or instantaneous phase, so I might have you do a sketch of something like that. That's one option. That problems like that were on the old exam, so if it's something that I would decide to put on there, it would be one of the types that I didn't put on your exam, but might appear on the old exam of those types, not the exact problem, but something where you have to show me what the instantaneous frequency is and maybe note what the peak frequency deviation is for that particular type of waveform. Working with the Bessel function tables, everybody, you maybe didn't do things correct with the numbers you looked up, but I think everybody looked the numbers up in the table properly. Not always used properly, but you found them in the table, so I'm inclined to not really want to spend any time on that. I am very interested in Carson's rule, though, so I say expect a problem on this. So that means you'll be using this in one form or another to work a problem. And for sure, it would say it would be part of the block diagram for the frequency division multiplexing, where you have to account for a bandwidth and a bandpass filter based on Carson's rule and peak frequency deviation or deviation ratio, one of the two. Narrowband to wideband conversion, we did have that in exam 2. I wasn't totally satisfied, but it wasn't really that part that was the problem. So I'm just going to go ahead and say no to that. Rather than saying not likely, I'll say no. It is possible that I'll have something on demodulation with like an ideal discriminator. Interference in both linear and angle modulation, just be a short answer question. And fundamentally, the differences are that in linear modulation, the interference, unless you're using envelope detector, if you're using, say, coherent demodulator, the interference just gradually takes over the signal and masks it over. If you're doing FM modulation, when you have strong interference, you reach a threshold point where the signal is just gone. And the threshold phenomena also exists in envelope detectors too. So I could ask a short answer question, and that's possible. Don't know, but it would be a short answer question like. I mean, I could also ask a fundamental question on what are the advantages of, I think that's, yeah, that gets down here. That's general performance of modulation systems and noise. Let me wait till I get down there. So phase locked loops, I'm not going to say likely, but I'll just say maybe. It would be a more advanced synthesizer problem. And I'm going to say in the phase lock loop, not too likely. Certainly not of the detail that you had on exam 2. Sampling theory, yes. Where sampling theory is going to actually come into play, it's not going to be like the bandpass sampling theory. You'll have to use it in, most likely you'll be using it in a time division multiplexing problem, which is coming up down the page here. So that's right down here, multiplexing. So that's about the only place that sampling theory comes into play, just knowing that if you had a 20 kilohertz high fidelity audio system and you wanted to process that through in a PCM system, you need to sample at greater than twice that highest frequency, and then that would impact the number of serial bits per second from that source that was getting digitized. No problems on this. Delta modulation, no. On delta modulation, yes. And primarily because it will be in TDM, where again you're setting up an analog source that's going to get digitized with so many bits per sample and that sort of thing. So down into multiplexing, I'm going to scratch out is not likely because I didn't give a TDM problem on exam 2, so it is likely in the final. It's a very simple kind of problem, but you have to draw the block diagram and then give me the serial bit rate. Quadrature multiplexing, what is it? It might be a question about what it is. That's where you're putting two sources of information, one on the in-phase carrier or the cosine carrier and one on a sine carrier. So it's possible, not super likely, but it is possible. It might be that it would be built into the FDM problem. So it could be inside an FDM problem. In FDM, this is a guaranteed problem because we didn't get, it wasn't on exam 2. So you will have one of those, and you had that in a quiz problem, and you had that, well, actually it was in the homework problem, and the solutions are up there for that. So that's kind of a roadmap as to what I'd be looking for in that. Or I could give you a problem where I draw part of the block diagram and I leave pieces out and I say complete the block diagram. See, I'm thinking out of the box right now. What am I going to do? That's an option I've never tried before. Finish something that's been started. And then we drop into the appendix and physical noise sources. The basic thermal noise is the only thing. The rest of this stuff is out. Oh, wait a minute. Available power. Let me not get too carried away there, because I just crossed through something that is utilized later. Shot noise, other sources, frequency dependence, quantum noise, but this concept of available noise power is used because that is where we establish the KTB thermal noise that ends up being in all the calculations we do. That's where the minus 174 dBm per hertz comes from, is the KT. So that is essential. And Nyquist's formula just kind of goes hand in hand with this, if it's a resistor network. And then the last topics, noise figure, measurement of noise figure test sets, no. Noise temperature, effective noise temperature, cascade of subsystems. Those things are rolled up into something on the final. Noise figure of an attenuator is the attenuation value. Then I'm going to try to put some simple propagation problem in there too. So that's why I kind of reviewed through the math for that right here. And on the digital communication side, from what you're learning in the project, it'd be very high level quantitative problems like I could ask you, what is an iPlot used for? What is a waterfall plot in digital communications used for? If you're looking at a waterfall plot like this, that's signal to noise ratio, and that's probability of error. So a truism for a waterfall plot is the theoretical error probability plot. Suppose that's the blue curve. You can't do better than theory, but when you have impairments in the system, you always push out to the right. So I could give you a plot, and I could say, if this is 10 to the minus fifth, and this is where your ruler comes in handy, and Chris, this is what you were talking about a few moments ago. You would you'd be looking at down here on the SNR axis how many dB out the actual curve is relative to theory. So that would be a hit for your link budget in that many dB that you'd have to add to the link to overcome the system impairment somehow or another. And I think I just talked about that down here, EB over N naught, energy per bit to noise power spectral density. It's going to be very simple concepts though. and you're going to have things at your fingertips, and that's why I put that appendix on the project too, because it's kind of just to give you some of the fundamentals in that, which I want you to have some knowledge of, so if that's where they stick you on your first job, you're doing measurements in the lab, you'll have had some exposure to it. When they say run these bit error rate or probability bit error curves out for us, we want to see if our system is working better than the last time we had it in the lab. Or you might be involved with acceptance testing when a customer's there on equipment that's being sold off. I'm out of time, and I don't have a glass of water nearby me. My throat's getting really dry, so I think that's a good time to stop. I will save this off and post it up on the What's New section, so it'll be readily available and viewable. Any other questions? I'm going to make my way back over to the web page and get ready to stop the video. Any questions before I bring the video down to a stop?
No, thank you.
Okay.